Hi, in this video, I'll be solving this really cool math problem from this year's Putnam competition 2024, and it's question A1. Determine all positive integers n for which there exist positive integers a, b, and c, satisfying that equation. 2a to the nth plus 3b to the nth is equal to 4c to the nth. In this video, in answering this question, I will be using just algebra, a lot of algebra, and some basic modulo arithmetic. All you really need to know is what modulo congruence means, and you'll be able to follow this video. All right, so we have a problem. Let's strategize first. Let's start with the equation they gave us. In the introduction, I mentioned modulo arithmetic. This is the reason why whenever I see a problem like this, I think modulo, divisibility. I have a power n positive integer, and I have positive integers a, b, and c, and the set of positive integers is infinitely large, right? But if I think in terms of modulo, or in terms of divisibility and residual when we divide, then I only need to worry about the range of numbers from 0 to the modulo minus 1. It's a much smaller set of numbers to be thinking about. So in my head, I'm thinking I should do modulo on this. Modulo what? Well, there's a coefficient of 2, there's a coefficient of 3, and there's a coefficient of 4, so I should think about modulo of 2, 3, and 4. And there's a power n. Potentially, I may have to think about modulo n, and maybe Fermat's little theorem might come into play. But right now, let's think about 2, 3, and 4. Wait, maybe I don't have to do modulo 4, because if something is divisible by 4, it's also divisible by 2. And as soon as I saw that, then I realized that, look, this term right here is divisible by 2. It's an even number. This term right here, because of the 4, is also an even number. And therefore, the term in the middle is also even. If the term in the middle is even, and it is equal to 3 times something, and 3 is odd, then that means b to the nth must also be even. Well, guess what? If b to the nth is even, then b itself is even. Because an odd number, if you raise to a power, it would have been odd. It would not be even. Then I can write it as 2 times some other number, b1. I have an expression for b. I'm going to plug it in. b to the nth is now 2 to the nth, b1 to the nth, and the whole thing is equal to 4c to the nth. Oh, look, I have a factor of 2, I have a factor of 2, and I have a factor of 2. I have a factor of 2 in every term I can divide throughout. Okay, that's even. That's also even if this isn't 0. So if n is greater than 1, then this is also even. Have 2 even terms, that means this a to the nth term must also be even, which means a is even. A is even, that means it's 2 times some a1. So far, so good. I'm feeling like eventually a, b, and c are all going to be even. I'm going to plug it in. I have a common factor of 2, so I can divide through by 2. This one loses 1 factor. And c to the nth. Check this out. This one is an even term because it has a power of 2. This one would also be even if this power right here is not zero. So I need to write down here if n is greater than 2. If n is greater than 2, then I have an even term, and the last term. So that means the last term is also even, giving me c is even, c is equal to 2 times some c1. Ha, plug it in again. And c to the nth is 2 to the nth, c1 to the nth. I see a bunch of factors of 2 that I can divide throughout. Divide by 2 to the n minus second right here. So the first term, I have a 2 left. And on the right-hand side, I have 2 squared, which is 4. 4 c1 to the nth. As soon as I arrive here, I realize that this equation is exactly the same as the original equation with the same coefficient 2, 3, and 4, except that the a, b, and c terms are now cut down by a factor of 2. Right? Each of them is just half of the original. That means I can start with the equation with a1, b1, c1 here, go through the exact same logic, and arrive at the same thing again, except that the a, b, and c are cut down by another factor of 2. And then repeat that, cut it down by another factor of 2, another factor of 2, another factor, and I can always do that. I will always be able to do that because no matter how much I cut down, it will be some sort of a and some sort of b and some sort of c. And that sounds impossible. That sounds impossible because, eventually I have to run out of factors of 2. But according to this logic, it sounds like I will never be running out of powers of 2. And that sounds contradictory. So I think I know my strategy now. What I do is I take out as many powers of 2 as I can out of the ABC, walk through this logic, and arrive at A, B, and C still being even, meaning there's still powers of 2 left to be taken out, and that's just a contradiction. So that's my strategy. My strategy is to take out powers of 2. But I can only do that if I go through this logic here. Eventually, I'll hit this step. And at this step, I can only continue on if n is greater than 2. Because if n is equal to 2, then 2 to the power n minus second will be equal to 1. And I will not be able to conclude that c is an even number. So I need n to be greater than or equal to 2. I'm going to take out all the powers of 2. And I prove that that leads to contradiction because I can walk through all of this and find out that there's still another power of 2 left to be taken. That was my scratch paper. Now here's my real paper. I must first specify that I'm working for now with the case of n greater than 2. And then I'll come back and deal with the case of n equals 2 and n equals 1 separately. Right, in the case of n greater than 2, I'm going to take out, like I strategized, I'm going to take out the most power of 2 I can. So let's 2 to the power k be let 2 to the power k be the highest power of 2 that divides all of ABC. Then what's left is, I'll call it some kind of A1. 2 to the k times A1. And since I've taken out the highest power of 2 possible, there may be some power of 2 left in A1 or B1 or C1, but not all 3 at the same time. At least one of them has to be odd, because if all 3 were even, then that means there's another power of 2 that I could have taken out. And therefore, at least one of the A1, B1, or C1 must be odd. All right, let's plug in the original equation, equation 1. 2 times A. A is 2KA1. So it's 2KN A1N like that. They all share the common factor of 2 to the KNs. So I'm going to divide that all throughout. I end up with all right, which is the same as the original equation 1, except that everything got cut down by a factor of 2 to the kth. Well, now I'm going to do just like I did during strategizing. I realize that these two terms are even. And that means this middle term must be even. But because 3 is odd, and therefore B1 to the n is even, which means B1 itself is even. Well, B1 is even, then I write B1 as 2 times something. Let's call it B2. Plug it in. Divide by 2. This is even. This is even. And therefore, A1 to the nth is even, which means A1 itself is even. Then I'm going to write A1 as 2 times some A2 and plug it back in. Divide throughout by 2. Since we're working with n greater than 2 for the moment, this is even. This is also even. And that means this one has to be even. Therefore, C1 itself is even. I have B1 even, I have A1 even, and I have C1 even. That's impossible. They cannot be all even, because up here I already took out all the powers of 2 that I could take out of A, B, and C. At least one of the A1, B1, C1 must be odd. But instead, I've just proven that all of A1, B1, C1 are even. That contradicts the condition store. Meaning for n greater than 2, there's no solution. There's no A, B, C that satisfies that equation. Great. So now let's take care of the case of n equals 1 and n equals 2. Case n equals 1. Then I take the original equation and I plug in n equals 1. I get 2a plus 3b equals 4c. This is totally possible because all it takes is something that adds up to a multiple of 4. Let's try 1. 2 times 1, that will be 2. Plus 3 times. Well, 1 doesn't work because 2 plus 3 is 5. How about 2? Yeah, that works because 2 plus 6 is 8. So that's equal to 4 times 2. So yeah, for n equals 1, A, B, C exist. For example, A equals 1, B equals 2, C equals 2. Great. Now all we need to do is to check n equals 2. When n is equal to 2, then I have this equation. plugging in numbers doesn't work, go ahead and try with a few small numbers like a equals 1, b equals 1, and you'll find out it doesn't work. All right, so for case n equals 2, it's not going to be nice and easy like the case n equals 1. Let's strategize first. I should do modulo arithmetic again. But this time I cannot do modulo 2. I cannot do modulo 2 because I already tried it. And when I was working with modulo 2 right here, I needed n to be greater than 2. Right now, I'm working with n equals to 2, so I know that modulo 2 is not going to get me there. Next number up is modulo 3, so let's try it. Modulo 3, this one is divisible by 3. This one is not divisible by 3, but I could make it divisible by 3 almost by separating out the 3c squared. So this part here is divisible by 3. This one, I can do almost the same thing, but the other way around, by subtracting a squared like that. And these are divisible by 3. That means if I put the a squared over here, that means a squared plus c squared must be divisible by 3. Must be congruent to 0 mod 3. But that means both a and c are divisible by 3. Why? Because in modulo 3, a perfect square is congruent to either 0 or 1. This one going to be 0 or 1 only. This one is also going to be 0 or 1. And I'm going to show it to you in a minute as to why. But a squared must be either congruent to 0 or to 1. C squared also must be either 0 or 1. Well, what combination gets you 0? Just these two combinations. Right? Because anything else gets you either 1 or 2, which is -1, not 0. So that means a squared and c squared are both 0 modulo 3, which means a and c are 0 mod 3, multiples of 3. So I can plug it back in. I feel like I can plug it back in and play the same game as I did before with modulo 2 with odd and even, but this time with modulo 3. But right now, since I told you that the perfect square has to be either 0 or 1 modulo 3, I'm going to show you why it is so. If I have a positive integer k, then it has exactly 3 possibilities. It could be congruent to 0 mod 3, or congruent to 1 mod 3, or to 2 mod 3. Or if it's 0 mod 3, then that means the square of it is congruent to 0. If it's 1, then the square of it is also 1. If it's 2, then the square of it is going to be 4. But in modulo 3, 4 is the same as 1. So yeah, a square of a positive integer is either 0 or 1 mod 3, cannot be 2. If you're not familiar with modulo arithmetic, you can think of, for example, you can think of k congruent to 2 mod 3 as k is equal to 3m plus 2. It's some multiple of 3 plus a residual of 2. And then if you square it up, you get 9m squared plus 6m plus 4. But 4 can be written as 3 plus 1. All of these are divisible by 3. So that means k squared is a multiple of 3 plus a 1. And so the residual is 1. All right, so let's go back to strategizing now that we've taken care of this prerequisite. If a and c are both congruent to 0 mod 3, that means they are 3 times some number. I'm going to write a as 3 times a1, not the same a1 as before. I'm going to use it for convenience. C is 3 times c1, and I plug it in. have 2 times a squared plus 3 times b squared equals 4 times c squared. I plug it in, so the c squared becomes 3 squared c1 squared. A squared becomes 3 squared a1 squared. There's a factor of 3 everywhere, so I can divide it out. These are multiples of 3. That means this must also be a multiple of 3. I'm going to move all the terms with a factor of 3 on one side. And factor out the 3. And that means b squared is congruent to 0 mod 3. B itself must be congruent to 0 mod 3. And b is equal to sum 3 times b1. So I'm going to plug it into this. Divide throughout by 3. And look, I've arrived back at the same equation as before. I got the same equation as before, except that every number is cut down by a factor of 3. So I can do the same strategy as I did for the case of n greater than 2. With the only exception of, instead of taking out all the factor of 2, I'm going to take out all the factors of 3. Same strategy as before. Before I took out all factors of 2, now I just take out all factors of 3. Let's go back to the case of n equals 2. Let 3 to the mth be the largest power of 3 that divides all of a, b, and c. Then each of a, b, and c can be separated out with the 3 to the m factor and the rest of it. So a is equal to 3 to the m times something. I'll just call it a2. Where a2, b2, and c2, at least one of them must be out of factors of 3. Right? Because I'm taking the biggest power of 3 I could. So one of them is out of 3s. At least one of them. Is not a multiple of 3. Is not congruent to 0 mod 3. Learning from doing the case n greater than 2, I know this is going to be important. I'll name it condition star star. Plug in 2. A squared becomes 3 to the 2m. A2 squared, same thing with b and c. I cancel out the common factor of 3 to the 2m. And I'm going to rewrite this in terms of multiples of 3. I'm going to move all the multiples of 3 to one side and the rest to the other side. And the multiples of 3, I'm going to factor out the 3. That means a2 squared plus c2 squared must be congruent to 0 mod 3. Since all perfect squares are congruent to 0 or 1 mod 3, the only combination that works is that both of them are 0, because there's no other combination of 0 and 1 that could add to 0. which means that A2 and C2 themselves are congruent to 0 mod 3. They are multiples of 3. In that case, I can rewrite them as 3 times something. Okay, good. I'm gonna plug it back in here. Have 2 times 3 squared, A3 squared. That's the old A2 squared. Divide out one of the 3's. I'm gonna move these 2 terms on the same side because they have a factor of 3. So that leaves B2 squared isolated on the left. And then on the right, I'm gonna factor out the 3. Telling me that B2 squared is congruent to 0 mod 3, which means B2 itself is congruent to 0 mod 3. And I have arrived at my contradiction. A2, B2, C2 are all congruent to 0 mod 3. And it contradicts the condition up here that says because I factored out the largest common power of 3 they all have, that at least one of them must be not congruent to 0 mod 3. Condition star star. So this contradicts condition star star. And therefore, n equals 2 is not possible. N equals 2 doesn't have a set of ABC that satisfies the given equation. So I did 3 parts. The first part is for n greater than 2, there's no solution. The second part is for n equals 1, there is a solution. And then for n equals 2, there's no solution. Put that all together, final answer. Only n equals 1 has ABC. There we go. That's the answer. I hope you had fun. Any questions or comments, please put in the comment section below. Like, share, and subscribe for more contents. And thanks for watching. Bye.